Okay, so in this talk, we will cover the topic of intelligent, optimized inference routing using a combination of smart prompt routing and distributed LLM serving. The two main components we use are something called a semantic router, in particular the vLLM semantic router, and the LLM-D distributed inferencing stack. So this is what our topology is going to look like. In this talk, we won't get into all the internal details. This is going to be mostly a high-level show and tell of this solution. So what is going on here? So we have an Istio-based Envoy gateway. This entire environment is running on a Kubernetes cluster. So it is mainly targeted for enterprise inferencing deployments, right? Enterprise-grade deployments. So there is an Istio-Envoy-based application proxy or gateway. It has a number of routing and load balancing functions, and it has two kinds of extension modules attached via an external processing interface. One category of extension module are model pickers and prompt processors, right? And the second categories are endpoint pickers. So model pickers, of which the semantic router is one, perform the function of taking a prompt and deciding which of X number of base LLM models is the best optimized to serve this particular request, and that could be based on cost or quality of performance and so on. So it's a model picking function. The second kind of extension is an endpoint picking function, which is that once we know that we want this particular base model, if I've got 4 different replicas of local LLM, say, serving that model, which would be the best replica I should go to? And the answer may depend upon not regular load balancing algorithms, but on factors like how are we disaggregating the prefill portions and the decode portions of that inferencing, or where is more of the KV cache state reusable based on this new prompt, right? And so essentially leveraging the hardware state for more optimized and inferencing. So we're sort of showing that the purpose of the solution is that it is possible to have a combined solution where you're doing both the model-based optimizations, model picking, intelligent model picking and routing, as well as intelligent endpoint picking, right? Okay. So we will also show that we can do this with backend LLMs being served from multiple locations. So you could have local LLMs being served from the same Kubernetes cluster as the gateway and routing functions. You could have also local LLMs being served from an adjacent cluster, which is in some way networked to the first one, or we could have LLMs hosted by a public cloud, such as the OpenAI.com, serving maybe one of the GPT-4 models. And this is exactly what we will demo today. So we will essentially demo the joint integration and solution of the Istio gateway, the vLLM semantic router, the LLM-D distributed inferencing stack, and 2 categories of backend LLMs, one being local LLMs served with vLLM in the same cluster, and one is publicly hosted LLMs. So let us now actually look at our setup here. Let me confirm that we are still recording. Yes, we are. So let's keep going here. So what do I have here? So I have working in Kubernetes environment. So let us look at the pods here. So we see that we've set up LLM-D first using the well-lit path orchestration guide, which you will find in the LLM-D website and repo. I will be adding links to both the semantic router and the LLM-D and Istio repos and websites so that you can follow these for more information. So following that well-lit guide, we've got this deployment where we've got the LLM-D endpoint picker running in a pod right here. We've also got the Istio gateway, the application proxy that front-ends these modules running right here. It is set to operate in an AI gateway mode using something called a gateway API inference extension. And then we have model services, which are in this particular case serving two local instances of the Quen model, which also are served using vLLM. So this is sort of your local setup. We also got the semantic router, which we will see is in its own namespace, and we see that there is a semantic router running as a router extension in that namespace. What we're going to do is we're going to look at category-based routing. So what that means is an incoming LLM prompt will be semantically matched to prompts belonging to certain categories, right? For example, math, science, business, biology, and so on. And we expect that there are some backend models which are better at answering questions in that category 1 and others in category 2. In real life, the use cases may be more like one may be a smaller model and hence lower cost of inference, and the other may be a larger model which has a higher cost of inference but is much more knowledgeable and well trained. So you could use this for a number of such scenarios. Another scenario could be, for example, an edge versus core distributed system, where you may want to service some inference requests at the edge of let's say a content delivery network or an inference delivery network, and have simple queries be answered at the edges, and then have more complex queries go to larger data centers running larger models, right? So you can use this in a number of real world cases. So we've got, like I said, the Quen pods and the OpenAI LLMs. So, but the categories that we've got are, for the purposes of this example, we'll say that we've got the business category of prompts related to business and computer science topics should get routed to the local LLM models, and prompts which are in the category of mathematics and pure sciences should get routed to OpenAI, right? So how do we configure the semantic router? We look at its config briefly here. Let me make sure I keep my call going. Okay, so in the semantic routers config, we've told it that, look, you will be routing to two types of backend models, a Quen family model and a GPT model. And then we map the the categories to those models. So we say, so for example, here we are saying that if your semantic search, which is actually a search in vector embedding space, right? If semantically the prompt falls into the business prompts category, then route it to the backend model Quen, right? And then if the semantic match of the prompt is closer to a math and pure sciences category, then let's see what it has been configured. So, for example, we've said that here, if it matches the math category, then route it to GPT-4o Mini, right? So math goes to GPT, computer science and business goes to Quen. Now that this semantic router has been set up in this way, we can go ahead and try some inference requests. Also, what we're going to do is we're going to go ahead and enable logging in both the semantic router and the LLM-D scheduler, so that we can see which component is active for different kinds of requests. So let us see the logs here for, I'm going to go ahead and enable the logs for, okay. So when we send the inferencing requests, we can see which of these components are active for particular kinds of requests. So let's send a curl. Okay. So we're running this in Kubernetes, and we are exposing an endpoint through the gateway at this IP, and we are calling the chat completions API running at that endpoint. And we call it using the OpenAI style API, except that the client has set the model to be auto, right? So what this means is the client wants the infrastructure to pick the best model for that request. And the question being sent is 2 plus 2 is what? So it's now up to the semantic router to decide semantically which category does this question best match, and send it to the model that has been configured to be the best backend for that category. Okay, and we sent it the question, and it got back a response saying 2 plus 2 equals 4. Okay, you're correct. And it was routed to the GPT-4o mini, this specific version. This actually went over the internet to openai.com. And remember that we didn't actually say that you want to route this request. The model was set to auto, but because we have a semantic router, it decided that this should go to the OpenAI. And so we see that the semantic router did work. And if you notice the logs here, we did see logging activity here. In fact, you will see also in the logs here that it did decide that this is a math question, and hence it selected the GPT-4o mini, even though the user just had said model is auto, right? So we've essentially done semantic routing through this use of the semantic router, but without using the LLM-D scheduler in this case. Now let's try another kind of prompt. Let's say the prompt is Linux is set to be an open source kernel because, right? And again, the model is set to auto. So semantically, this would appear to be more of a computer science or business kind of a question. So presumably this should route it differently. Let's see whether that happens. And we saw activity on both. So apparently both schedulers were involved. Let's see where the response, it says, came back from the Quen model. So this time the semantic router decided that this question semantically matches one of the categories that are mapped to the Quen model. And that's where the response came back. And yes, there was some reasonable response to why Linux is an open source kernel. So you can see that in this case, the semantic router, and we can verify this from the logs, it selected the model Quen because the semantic match decision was computer science. So and hence it selected Quen. And then it noticed that because Quen is a local model with multiple instances, it then did a second level of scheduling through LLM-D to pick which of the two instances of Quen is best suited for this request. And then the LLM-D scheduler kicked in, for which we see the logs here, and we see that it was doing the scheduling here, and then it picked one of the specific endpoints at this particular IP address. And in fact, you can confirm that those 10.2.40.016 is one of those Quen pods. So this time we saw that both the schedulers, the model picker and the endpoint picker, were operated in sequence in order to pick the right pod to serve the LLM query. So again, that essentially illustrated the fact that we've been able to do both cloud routing to cloud LLMs as well as routing to local LLMs, and use combinations of the model routing as well as endpoint routing. As a final point, we'll simply check another case where the user does not want to do model routing. The user has already decided which kind of model they want the query to go to. So let us, for example, say that The user says, okay, I want the question 2 plus 2 is, but explicitly specifies the model as GPT-4 mini, right? So there is no auto routing here. And sure, it went ahead and just, you know, there was no intelligent routing decision done. It straight away went ahead to the OpenAI endpoint and gave the same answer as before. Um, and we can also, one other thing to check note on this case is that um, well, in the auto routing case, really, it is that when a user is sending a query, they do not know whether the semantic router is going to choose to send it to a public cloud or local LLM, or which public cloud. So the user hasn't actually injected any authentication or API keys. So it is up to the routers and the gateways in this system to have those API keys, so that when they access public APIs, right? These are not free APIs. You have to have a developer account and use the API key and get charged for it. But that process is all handled by the routing and gateway process, right? The user just sent a query, and it was the infrastructure's decision to send it to OpenAI, and hence the infrastructure injected the OpenAI API key. So there's a central place for locating all the API keys as well, right? Yeah, so that's kind of it. So essentially, to wrap up, we showed that we can have uh, multiple levels of optimization when serving inference requests, both model picking as well as endpoint picking. And these two important projects, the vLLM Semantic Router as well as the LLM-D, are key to making this happen. And we've shown that they can work together very nicely in a unified solution along with gateways such as Istio. So that's it for this demo. Thank you.